So you have set up the virtual domain as this for your textile composite. You have the right material of the yarn and you know how to apply the correct boundary condition for your simulation. But do you know that if you do not assign correctly the material rotation to the binder, the weft and the warp yarns, then the whole model prediction will be disastrously wrong. Relax, I will show you how to do this in this video, so let us sit back as we get started with this modeling. Hello, my name is Dr. Michael Okreke. Welcome to CM Videos. This is a YouTube channel where we try to help you create effective computational modeling solutions to whatever computational problem that you're dealing with. The key thing we need to consider here is that ultimately you're going to get a curved fiber that looks like this. So there is a global reference frame that is attached to the system here. And with this global reference frame, okay, everything is all around the x-axis. So this is x-axis, this is x-axis, which is the main fiber direction. However, this is not a pure x-axis behavior. So if you really want to specify the properties of this correctly, you need to then specify a coordinate system that tracks the variation of the curvature of this system. And so you're looking at things like this. And this will be what we're calling a material coordinate system. Within ABAQUS speak, the global coordinate system tends to have this XYZ labeling to it, while the material or the local coordinate system tends to have this 1, 2, and 3 labeling to it, where 1 corresponds to X, 2 corresponds to Y, and 3 corresponds to Z. So if you look at here and there is a correlation between the two, at least at the start of this fiber. But as you start moving along the fiber, that material coordinate system starts changing until you get to the end. And so what we want to then do is to specify this material coordinate system for the fiber that in this case is transversely orthotropic. And with that, we can then go ahead and specify its material properties and it will be correct. So let's think more specifically about the textile composites would happen. So let's start with this. So this represents 3 types of yarns that make up textile composites. So here we see the binder, which runs in this case. So this material is a 3D orthogonal composite, and then the warp and the weft yarns. So each of these would have to have their individual material orientations if we are going to model this correctly. So in principle, what that basically means that the global coordinate will remain. So this global coordinate would not be required for specifying what's happening in the local coordinate system for this. Now, then we begin to have the local coordinate system for the yarn. So what will happen in this instance for the binder would be you start off with this orientation, which is coincident with this, and then as you travel along the length of the fiber, the primary axis being the one axis, you notate that the one axis keeps changing as you move along. The normal axis, which is the 3 axis or the Z axis, continues to remain normal across the material. However, the 2 axis will also rotate along as you travel across the material to the end. So we need to then specify a mobile or a variable material orientation that tracks the movement of this yarn in this direction with the primary axis acting the way it is. Then we'll also need to recognize that there will also be a different system for the other weft, and then there will also be another one for the warp. So all these need to have their individual specification, and this is kind of what we're going to be doing here. So you end up having this set of material coordinate system, one for the binder, another for the weft, and the other one for the warp system. And that's really what we need to specify if we are working with a textile composite. If you really like this kind of content that I'm presenting here, please, I do encourage you to sign up to this channel so that when content like this are made, you'll be the first to see it. So let's now go into ABAQUS as we get started with this modeling. So here we are in ABAQUS, and what we see here is basically the represented volume element for the 3D orthogonal textile composites. So clearly the binder, they run this way, and then we warp and the weft yarns are all acting in this way. So it's been created, and then what you see here is the metrics. So what we want to do here is, once we've set up this model, we want to then apply these local coordinate systems to then give it the right kind of orientation in order for it to be able to behave correctly within the simulation. So what I've got here is basically within the part module. So I've got the binder, the metrics, the orthogonal 3D, which is really the assembly of every other thing, and then we've got the warp bundles and all that. Those are not important. Really what I want us to focus on is the orthogonal system here. So within the orthogonal system, that has all the setup that are associated with it. So if I switch this to section, so you can see all the different sections. And what we then want to do is to try and isolate what is going on and then pick individually each one of them and then apply what we need. So let's start first with the binder arrangement, which is the green one here. So what we're going to do is that if you look here within the system, so I'm going to select the warp and then go to the top here and click remove selected. So that goes away. I'll select the metrics and click there, remove selected, the metric goes away. And then the warp system, I select there, click. So that leaves us finally only with the binder, and this is the binder that then we're going to use to specify the coordinate system attached to it. So what we're going to look at in the orientation system here, so if you click on this point, now it gives you the option to select the region you want to apply the material coordinate system. So I want all of that to inherit the same coordinate system, which is the binder, and then click done. Now it gives me the option of selecting how I want to do this. So either I use the default XYZ coordinate system in a global sense here or something else, but clearly in this case we can't use the default because that will be different. So if I then click on that, now the option is to work with the global. So if we zoom in here, you find that okay, it starts off here, but then it's not really recognizing the fact that the one axis should actually be along this length. Then it kind of walks around here and then it fails in this. So working with the global reference, which is consistent with this, is really not the right thing. So we're going to change that by tweaking this to discrete. So now in the discrete, there are two possible things we need to do with the discrete system. So again, under here you've got the normal axis and the primary axis, so we need to specify that. Currently it's undefined, so I'm going to tick there to give me the option of how I'm specifying this. So the first instance in the third axis, which is the normal axis, or the 3-axis in this time, means it has to be consistent with the z-axis there. So I need to specify that. So if I tick on that, then I'm going to select this surface here. So if I click on that, so that gives me that surface. So this will be the outward acting normal direction, so the surface of interest. And then I will now, so what we now have here would be, okay, the system is acting there, and you could see the outward acting normal is acting in the way it should be, and everything is fine in that scenario. So what we then need to look at is what happens in the edge. So the primary axis would be the axis that obviously runs along the fiber all the way through to the end. So I'm going to define that by selecting, let's say we select the inside one. So you select the inside one here and maybe press down shift control select there and go back onto this other end and select shift control there. So press down shift means you can select all of that at once. So what that means that you're selecting the whole region in one continuous flow, and then click done. So now it's picked up correctly that okay, this is my predefined one axis acting in the right direction, and everything looks all right as we'll expect. And then we can click continue and then click OK. So if I then go back here and look at what I've done, so clearly the one axis is acting correctly. So you see the one axis goes this way and goes back in, and then comes back here and then goes around in the correct way across. So everything looks all right with this particular instance. Now the next thing, we need to replace some of these things. So if I replace every one of them, now the next thing is I'll need to think about what's happening with the other systems. So what do we do? So I now have to hide the binder, probably hide the metrics, and then maybe the warp as well, so leaving only this particular system here. But then this is really very interesting, because what we find here is that we've got a system and we need to specify what the x direction would be on this. So clearly it wouldn't be in this direction. The one axis is the axis along the fiber, so we need to create a new coordinate system for that. So I'll click on this, which is a create a new coordinate system, and I'm going to call it, okay, so we're working with the warp CSYS, so a rectangular coordinate system. Now what it's saying is that how am I going to specify that? So it says select a point of origin. So let's say probably I could select maybe this point here. So this is my origin, select a point on the x-axis. So this is my new x-axis, so I'll select maybe a point there to present my x-axis, and a point that will be my y-axis, which will be here. So what this is showing us here now, that we have a clear picture that tells us what the new axis would be for that. So once we specify this local reference frame, this coordinate system, then we can then attach it to this particular case, so that our new one axis will be the axis that's along the x-axis. Even the global reference is acting in this way. So again, we go back to there, and now which region do you want to apply this? So I select everything there and click done. But I'm not going to work with the default system here, because this is only for the global reference frame. Somewhere at this other end you have the datum CY system. So I'll select the warp system, okay, so that's fine. And automatically everything is fine. So my coordinate system now is attached to this reference frame, and then we'll click OK. So if we then go back and look at that more closely, so what we see here is that it's correctly specifying that this is our y-axis, okay, this is our y-axis, and then the plane that goes this case is our z-axis, which is what we'll expect to happen with the warp system. So it is now inheriting a different coordinate system from the global reference, because this is what we want to do, because we created a local reference frame for that. Okay, so what we're going to then do is to replace everything. So if I replace everything, okay, so the next thing we need to do is to work with the other orientation. So I'll select the ones that we have done and leave only the ones that is undone, which is the warp system, and remove that. So that leaves only this instance. Now, like we did before, we need to also create a local coordinate system for this. So by clicking on this, so here I'm going to call it, or the weft C system. Okay, so we'll work with that. Then it says, okay, what are we trying to do? So I'll select, so if we just zoom in here, so I could select, let's say we select at this point, okay, and then what will be my x-axis? My x-axis will have to act along this length, so I could select maybe this point, and what will be my y-axis? I'll select that point. So what this is showing us again is that you've got a coordinate system where the actual x-axis, which is along the length of the main longitudinal axis of the yarn, is acting this way. This is the y-axis, and then anything planar that extends outward will be the z-axis. As usual, we click on the orientation, select the whole system, click done. Now what it says, okay, our datum list, we select this one, okay, the weft C system. So we select that and then click OK. So, and then that's done. So what this has done, if we go and look at this last case, so we see that it's showing us correctly what we expect. If we zoom in, so the one axis is acting in this direction, the two axis is the other in planar direction, and anything outwardly acting is the z axis. So we've got all of that, and then let's just replace everything back into the system, and then we get it in the window. So what this means, that now we have the coordinate system for the binders the way they need to be, the coordinate system for the warp the way they need to be, correctly specify the coordinate system for the weft the way they need to be. And this is really important if we're going to do textile composite modeling, because you need each yarn to inherit a local coordinate system. And then once you've got all these, then you can carry on with the modeling, specify the material properties, and then the model will work out well. So let's say you are wondering how you can do this for, let's say, a curved fiber unidirectional composite. This will be a video that can help you do that. And if you want to learn a little bit more from the ABAQUS tips and tricks videos that I've made on this, please, again, this is the video that can help you. Thank you for your interest in this channel, and if you haven't subscribed, please do subscribe. Thank you, and see you in the next video.